Well, thank you very much for being here. Thank you very much for organizing this and having me here. My name is Giuliana Cosentino. I am an astronomer here at the IRAM in Grenoble, where I do my science, but I'm also part of the IRAM ALMA ARC node here, and I'm also part of the NOIMA Science Operation Group. As Italcon already has presented very well, within the AtLAST frame, I'm also co-chairing the working group 118 together with Italcon. So today, I would like to tell you about what my science is in this under this big umbrella of the emergence of prebiotic chemicals in interstellar space. But I also would like to tell you why AtLAST is actually very much needed to continue going on in that direction. No. Yes. Okay, so we have always been told that stars form in molecular clouds, and we all sort of believe that. But under this sentence, there's a lot that we don't know. There's a lot of dust under the rug that needs to be dust off. First, if we look at this partial infrared view of our own galactic plane, we see a lot of dark patches. These dark patches is what we call molecular clouds, and these are objects that are very dense, with density higher than 10 to the 3, 10 to the 4 centimeter minus 3. They are very cold, down below 20, 25 Kelvin, as Tasco was saying. And they have visual extinction that are very high. They can be up to even more than 100 magnitudes. But what I wanted to point out is that in this already partial view of our galactic plane, there seems to be quite enough of them, quite a lot of them. But we also know that despite being so much material, of all the material that can be converted into stars, only 1 or 2% get actually to form stars in a free fall time in our galaxies and in galaxies like our own. We say that the star formation efficiency of these type of galaxies and of our galaxy is low, and that the star formation is an inefficient mechanism, that there must be something that prevents these clouds, this material, to form a star. But at the same time, we do see stars. So we know that molecular clouds do form stars. So there must also be something that makes this cloud collapse and form stars. We don't know to date yet. We have an idea, we have theory, but we don't have a black and white answer. So the question that I'm exploring is how is star formation ignited and hindered in molecular clouds? What are the mechanisms that regulate star formation in these objects? And the question that I'm exploring is whether large-scale interstellar shocks may play a role. Interstellar shocks are pressure-driven magneto-hydrodynamic perturbances of the medium. And we look for the large-scale ones because we want to see shocks that are able to affect the full cloud, so at cloud scales, so from parsec to a few parsecs. Where can we find these shocks? Well, shocks are kind of ubiquitous. They're in many places. The ones that have been historically studied the most are probably molecular outflows. They are the ones driven by protostars, but they're also found in H2 regions. They're also associated and thought to be able to develop at the interface between the collision between molecular clouds, so in cloud-cloud collisions. And they're also associated with the expanding shells of supernova remnants, like this one. And these are the type of objects that I'm going to focus on today. So we know that supernova explosion are the last stage in the life of stars that are massive, more massive than any time our sun. But these objects, they live their life most likely not in isolations. It's a bit controversial, but it's believed that is either they end up their life where the molecular cloud is still there as a dispersed death, but in any case, when they explode, there's still the interstellar medium around. So when they explode, they leave behind this beautiful shell of material, like the one you can see on the left side of the screen, I believe. These shells expand into the interstellar medium. They are make plasma, energy, and material, and they encounter in the trajectory material that can be more or less dense. depending on several conditions. Among these, the density of the material encountered, but also the velocity of the shock associated with driven by the supernova. We can have different effects. It has been theorized that if the density of the gas is low enough, and if the shock velocity is large enough, we can have the material can be dispersed and displaced. And in this, what happens is that the star formation is prevented to happen, and this is known as negative feedback. On the other hand, for supernova remnants that are a little bit older, and in which the velocity of the shock has slowed down significantly, and if the material is relatively dense, what can happen is that these clouds get further compressed, and in the compression layer may develop the condition to form new stars, and new generation of stars may actually occur. This is known as positive feedback. It is believed that the interplay between the negative and the positive feedback may actually have an important role for regulating star formation in the galaxy. But more than this, it is, as Zaskun has presented already in a very convincing way, it is believed that the supernova remnants may have had a role also in the formation of our own sun. So it is believed that the protosolar nebula was affected by at least one supernova remnant, and that, as Zaskun was saying, the material the protosolar nebula may have been enriched in fresh chemical compounds by these supernova shocks, and that these compounds may have been then inherited by the protosolar disk and eventually by our own planets, and are now the very base of the chemistry of life as we know it. So it is important to study the chemistry of molecular clouds that are impacted by supernova remnants. To do that, we have our starting point has been to focus on a very peculiar molecular cloud that has a very long name, is G034.77 minus 00.55. For the sake of everyone, we will call this cloud Cloud G. And the specialty of this cloud is that it is in between a supernova remnant and an H2 region. Actually, the cloud is being the filling of a sandwich. On one side you have the supernova, and on one side you have the H2 region. And the supernova is the well-known supernova remnant W44, which is a 20,000-year-old core collapse supernova remnant. So as first step, we have studied the interaction between the cloud and the shock interaction between the cloud and the supernova, which is seems to be occurring in this particular area in the orange square. We have seen what you can see on the picture is a zoom-in view in which you have in white shadow the cloud. This is the mass surface density mass of the cloud, higher than 0.1 gram centimeter minus 2. The orange contour are the silicon monoxide 2-to-1 transition mapped with ALMA. In this case, we had already observation with the IRAM 13 telescope. And what you can see in color scale is the channel map of the SIO emission that so basically tells you where the gas at a certain velocity is located. So what we saw is that the SIO emission, which is, so why we use the silicon monoxide? Because silicon monoxide is known to be a very good tracer, a unique tracer of shocks. So in order to be produced, you need to release a silicon in the gas phase, and this occurs when you have a shock that processes the gas. So what we saw is that the emission in this direction, I don't know if you can see my mouse, in the obliquous direction is 1 parsec extended over 1 parsec, and that the bandwidth of the SIO was relatively small, so 1 or 2 kilometers per second most. We also saw that the emission seems to be approaching the cloud at a velocity of roughly 46 kilometers per second, and then plunges into this arch-shaped ridge at the edge of the cloud, decelerating down to a velocity of roughly 39-40 kilometers per second. So this place seems to be one of the best to look at if we want to understand how the shock is affecting the chemistry of the molecular cloud, and how this compares to star-forming region that we know and our own solar system. So to do this, what we have done is to build up a large spectral survey that goes from 7 millimeter to 3 millimeter and 1 millimeter regime, using several instruments, among these the IRAM 30-meter telescope to obtain the 3 millimeter and 1 millimeter, APEX to pinpoint certain molecules at 1 millimeter, and the IRAS observatory to cover the 7 millimeter band. We, as you can imagine, this, as Itzasco was already telling us, most of these molecules can be quite faint. Therefore, these are expensive observations that has so far prevented us to go very deep into the mapping, and so we have opted for single pointing observations. So, for example, this is one of the 3 millimeter spectra that we obtained toward the cloud. As you can see, it seems to be very rich. So, what we did, this is a zoom-in view of the cloud in the infrared. As you can see, we have mapped 3 regions of interest, which are named the shock and the ridge, which are 2 positions across the shock front, and the clump, which is instead a very dense region adjacent to the shock. For few of the transitions we are interested in, we also have spectra in 2 other positions, which are named G3, which is a massive core within the cloud that was already known, and what we call the ambient, which is a region of the cloud in which there's no ongoing star formation, and there is no shock. The shock, we believe, has not penetrated there yet. So this is sort of our control region. So the first step in our study to understand better the chemistry of this shocked gas at the interface of the interaction was to study the deuterium over hydrogen ratio as the ratio between the column density of the N2D plus and N2H plus. This is known to be a tracer of dense and cold gas that has the highest potential to form stars. So the D over H ratio from these 2 molecules is known to go from the starlet to increase from the starlet to prestellar phase of a core up to the point in which the protostar has the onset of the protostar, in which the material is heated up. And what happens is that the carbon is released into the gas phase again, and the chemistry of the carbon takes over. So this quantity then goes down. So we calculated this quantity using Macuba, which is a tool developed by several people, mostly in Madrid, at the Center de Astrology. And what we do is that basically we model in local thermodynamical equilibrium the line profile of both molecules. And what we did is basically to compare the obtained D over H ratio values with the one of reported in literature for several objects like low mass and high mass dark object in which there's no protostars, so starless or prestellar, and the equivalent, the high mass equivalent, and then also protostellar object and infrared dark clouds. So what we saw is that what we have named the clump and G3, they have a similar D over H ratio of the order of 0.1, which is very high, indicates material that is very dark and is consistent with both low mass and high mass starless cores. But also the 2 positions across the shock front, which we named the shocked and rich, also have a D over H ratio that is around 0.05, 0.07, which is also relatively high, and is consistent with low mass starless cores. But most important of these values are enhanced with respect to our control ambient region, in which we do not detect any any N2D plus. We wanted to understand if this deuterated material that we find adjacent to the shock is a slab of material that has been simply fast cooled down, or if it is organized in little cores, in clumps, and cores that may be able to lately form stars. So we want to understand if this deuterium emission, deuterated emission, is coming from little cores that are the very first step in the formation of stars. So we have used the ALMA to map the N2H plus 1 to 0, and this is the image that you see. Again, the magenta contour is the outskirts of the cloud. The black contrast is the silicon monoxide with ALMA, mapped with ALMA. And now in color scale, we have the integrated intensity of the N2H plus 120. What we saw is that the emission, especially across this dense ridge immediately adjacent to the shock front, seems to be very clumpy. We used the dendrogram and calculated the mass of these little clumps with the course that goes from 1 to up to 12 or 15 solar masses. We also calculate the virial parameter of these little cores, and we find that they have values that are consistent with a scenario in which this object may collapse to form new stars. We continued, actually, the next step is to obtain N2D plus 120 emission, and we have done that with NOEMA. We have obtained this beautiful map, but this is a very, very, very initial cleaning on my side, so I need to improve this, and it's a very much a work in progress, so stay tuned. Okay, so we want to go even more complex than this, and we want to look at complex organic molecules and more deuterated species. So considering the cores that we found, we focused on this region here, which is the clump in the previous image, in which there seems to be a lot of these cores, and this seems to be the most massive in our sample. As you can see on the left side of on the right side of the screen, we have compared the location of the clump with the infrared images of 2, 8, 24, and 70 micron. And this seems to be a very dark region in which we see no obvious indication that there are protostars there already. So what we did is to look for new, more deuterated species toward this region at 3 millimeter and at 7 millimeter. And to compare the value of the overage ratio that we got with those expected in different environments, such as low mass prestellar and starless cores, low mass protostar, high mass infrared dark clump, high mass protostars, and also comets, because some comets are believed to maintain the information on the chemical composition of the pristine environment of the protosolar nebula. So in these plots, what we see in gray is our value, the value where we calculated, and then in the different columns, the different environment that we compare with. We saw that our values seems to be relatively compatible with the one that you measure in comets. We also compare to the other object, and it seems that this object may be able to form low mass, point toward the idea that this may, if they develop into stars, they would be low mass objects. I wanted to also point out that we were able to detect deuterated methanol. Methanol is the very first step into the formation of complex organics, and this molecule has been detected in a very few environments. We also looked for complex organics molecule toward this region. We detected CH3CN, CH3SH, CH3CHO, and CH3CCH. We compared the abundance with respect to methanol to, again, environments that are representative of low mass core, prestellar and starless core, but also protostars and comets. And again, we found that our column density seems to be consistent with the ones found, for example, in comets and in mostly low mass objects. More recently, and when I say recently, I mean I submitted the paper yesterday. We also looked at the presence of phosphorus-bearing species in the shock of supernova remnants. We are looking now at two supernova remnants. One is W44, which is the one I've been talking about, and the other one is IC443, which is known also to be a very textbook case of supernova interacting with a cloud. The difference is that the supernova is supposed to be is believed to be a little bit younger than W44, and the cloud into which it's plunging is debating whether it's a dense cloud or it is a translucent cloud actually. So as you can see from the spectrum, in which we show in black the PO plus 2 to 1 emission, and we see that we detect significantly the PO plus emission toward both, and that this seems to be correlated to the emission of the SIO, which instead is shown in green. Surprisingly, we do not detect any PN. In the few detections that there are in literature, we know that PN is observed to be brighter than PO plus usually, but we do not detect anything above the detection level in our spectra. Here in the bottom plot, we compare the PN upper limits that we obtain with a sample of different environments that was presented by Fontani and Minini and Rivilla in several papers. The abundance of PO plus that we detect, on the other hand, is consistent, at least consistent or a bit below the one of the detected, for example, by Victor Rivilla in the Galactic Center, in the same cloud that the Zascom was presented before. But in any case, we detect PO plus emission that is enhanced with respect to that detected by Samantha Cibelli toward a shocked core in the Perseus molecular cloud. Now, we have sort of hit the limit, the technological limit with these observations. We have observed one band at a time, mostly. Is it true with the IRAM tertimeter you can observe multiple band, but you basically give up half of your bandwidth, which means that you still need more tuning. As I was saying, for problem of computation of integration time, we are opted for single point observations. We have reached sensitivity of few millikelvin, 3 millikelvin. We want more if we want to detect molecules that are even more complex and fainter. And also we have had to compromise with a spectral resolution of the order of the kilometer per second, which in some environments may actually be quite good. But for this kind of emission, in which the emission is few kilometers per second wide in the line width of the spectra, this prevents us most of the time to study the kinematics and see, for example, how the kinematics of this object is connected to that of the shock or that of the cloud. So what we need is simultaneous multi-band observations, large field of view that allow us to see the whole supernova remnants at once, because we were very lucky and we know where the interaction is going on, but this is not the case for all supernova remnants. We need very high sensitivities because we want to detect molecules that are complex and most likely subthermally excited. And then we want a spectral resolution that allow us to study the kinematics. So what's next? All this can be done. Our hope is that AtLAST will allow to do all this, and we can do this with a multi-beam wide bandwidth heterodyne array on AtLAST. To give you a flavor of the improvement, we want to go from this to this. So this is a meerkat image of the whole complex in which the full W44 supernova remnant is embedded, and the red stars is basically where our cloud is located. And it's more or less what we are seeing right now with the spectrum up there. To give you a comparison, the full survey of our W44 source took more than 300 hours in the 5 to 3 pointing. This is more or less 3 small IRAM 30-meter large programs. And this can instead be, with the sensitivity estimator, tells us that this can be done more or less in 50 hours, maintaining a beam size that is comparable to the one of the spectra that we have now. So, my conclusions, can supernova remnant shock impact molecular clouds? Impacting molecular clouds set the physical condition to form stars. I haven't focused very much on this because I talked a lot about the chemistry, but yes, we see evidence that the shocks can cause a density enhancement sufficient to ignite star formation, and we have seen it of core formation at the shock interface. Can they affect the chemistry? Well, it seems so. We observe a lot of complex organic associated with the shock. The ORH ratio that are enhanced across the shock and comparable to the one that you will find in the region, and chemical molecular abundances that are connected to the one in our of comets. Can they do it often enough to affect the formation in galaxies? Well, of course, an object is not going to give us the answer, but we have initiated a large program, of which I haven't discussed much for a reason of time, which is called the SHREC. And the idea is to pinpoint the interaction between supernova remnants and molecular clouds to be followed up and give us a much larger sample. AtLAST will be absolutely groundbreaking to be able to do this at statistical significance. And with this, I am done.